Hello, this is Mr. Waters again, and I'm going to be doing some examples on, this is on page 669 of the homework. We're going to be identifying the conic represented by the polar equation, and we're going to describe the position of the directrix. Now let's just say that we're talking about this polar equation. R is equal to 3 over 4 plus 2 cosine theta. Okay, now, so if you look on page 666, there are 4 different variations that this polar conic equation can come into, can be in, depending on whether it's oriented vertically or horizontally, or depending on the position of the directrix. This equation, though, can represent any of the 3 kinds of conics that we deal with, or any of 3 kinds of conics. The ellipse, if the eccentricity is less than 1, a parabola, if the eccentricity is equal to 1, or a hyperbola, if the eccentricity is greater than 1. Now remember, the eccentricity, what that is equal to C over A, where C is the focal distance and A is the vertex distance. Okay? All right, so anyway, so if you look at the formulas on page 666, you'll see that in those formulas, in the standard form of the polar equation for conics, that number there has to be equal to 1. So the first thing we want to do in order to figure out what kind of conic we're dealing with here is transform that equation so that this is equal to 1. Well, you can see if that's going to be, in order to make that 1, we've got to divide that by 4, basically divide everything by 4, factoring a 4 out of the expressions or the numbers on the top and the expression on the bottom. Well, that's going to look like 4 times 3 over 4 on the top, and then 4 times 1 plus 1/2 cosine theta, where 2 divided by 4 is equal to the 1/2. Okay, so the 4's, of course, cancel out, and we get R is equal to 3 over 4 over 1 plus 1/2 cosine theta. Well, we can see from this that E, if we look at the formulas on page 666, E is equal to 1/2, which makes it less than 1, which makes it an ellipse. So our shape here, our conic, is going to be an ellipse. Okay, now we also want to calculate the second part of our process here. So this was the first part, to render the equation in the standard form. The second part here is we're going to calculate E, and then we're going to calculate P. Well, P comes from the value on the top. On the top, this expression, according to our formulas on page 666, that is equal to E times P. So E times P in this particular formula is equal to 3/4. So we already know that E is 1/2, so it's going to be 1/2 P is equal to 3/4. We multiply everything by 2, right? And that's going to give us P is equal to 3 over 2. Okay? Now remember what so P is equal to 3 over 2, and that is the distance from the pole, from the focus, which is going to be at the pole of the polar graph, to the directrix. It's 3 over 2 units. Cosine indicates that it's going to be horizontally oriented, where if it had been a sine, it would be vertical. So cosine tells us that it's horizontal. And since it is plus in the equation, that indicates that the directrix, or rather the pole, which is where the focus is 3/2 units from the P to the right. So the directrix is 3/2. This should say directrix there. Is 3/2 units to the right of the focus. So directrix to the right of the focus. And we can put some of that information on our polar graph now. So this point right here, that's the focal point, or one of the focal points of the ellipse. The directrix is 1.5 units to the right, according to P. So that's 1, so about here. Now since the ellipse is horizontally oriented, that means, and that's not very straight, that means that our directrix is going to be vertically oriented right here at 1.5. So we know that we've identified that the shape is an ellipse, and now how do we describe the position of the directrix? Here's what we're going to say. Okay, the position of the directrix is 1.5, or 3/2 units to the right of the focus, which is the right there, which is going to be where it's the polar origin of the graph, but it's also one of the two focal points of the ellipse. And the directrix, D for directrix, is perpendicular to the polar axis, because the polar axis, of course, is right here, pointing to the right, always horizontally oriented, and you see that our directrix is like that. Now, as to where our ellipse would actually be, it's going to be oriented something like this. The other focal point right about there. Anyway, if you want to get a really good picture of that graph, the equation that we got, that's this one right here, onto your graphing calculator. Okay, now let's try another one. Okay, now what I'm going to go ahead and do and erase some of this. Okay, you can go back and replay the video if you want to see that again, but I want to make some room here. Okay, for another conic, we'll leave the polar axis right here. Okay, there's the pole. What if we had, let's just pick another one to do. Okay, let's say that we had a conic like, say something like R is equal to 6/3 minus 3 sine theta. Okay, that I think will do it for us there. That's a pretty good one. Okay, again, you see that that's not in polar form, or it's not in standard form. That's got to be equal to 1. So what we'll do is we'll divide everything. As you can see, we're going to have to divide everything by 3 to put it in standard form. And that's going to give us, over here, R is equal to 6 divided by 3, that's 2. 3 divided by 3 is 1, 3 divided by 3 is 1, so we've got 2 over 1 minus 1 sine theta. Okay, well we can see here from the equation E is equal to 1, so that means it is a parabola. Okay, and since E is 1, the top, that's E times P according to the formula, is equal to 2. E is equal to 1, so 1P is equal to 2, so P is equal to 2. So that means that the distance from the focus to the directrix in this shape is, in this parabola, is equal to 2. Okay? So what else do we know? Well, let me see. What else can we identify here? Well, we can see that it's a sine. Sine means that it's going to be a vertically oriented parabola. And the minus there, according to our formulas, indicates that that means that the directrix is going to be located below the focal point. Okay? So, the sine tells us that it is vertical. That is an up and down, either facing up or facing down. And the negative on the inside there indicates that the directrix is below, P units below, the focus, which is at the polar origin. So we go back up to here, back up to our graph, polar graph with that information. Okay, so up here, this right here is the focus. Okay, and P was 1, and that's the focus of the parabola. P was 1 unit, so that's going to be right here. Okay, 1 unit, and the minus meant 1 unit below. Now that's the focal point. Okay, or rather, that's where the directrix is, I mean. So the directrix is going to be horizontally oriented like that, since the parabola itself is vertical. The vertex of the parabola is halfway between the focus and the directrix, if you remember your parabolas. So it's facing up. So there's our horizontal or vertically oriented parabola facing up. Now let's kind of go down here and summarize the information. And you can see here is the polar distance of 1, distance from the pole to the directrix. Okay. All right, now, what did we, okay, so let's make sure we summarize the information like we're supposed to. Okay, so the first thing is we see, oh yes, it's a parabola, that's the kind of conic. Okay, we're supposed to describe the position of the directrix. Well, the directrix is 1 unit below the focus, comma, and is parallel to the polar axis. Okay, if we go back up here, we can see why we say parallel. If the polar axis is horizontal and the directrix is horizontal, that means, oh yes, they're parallel to each other. Okay, so this is our final answer here about what it is and how the directrix is oriented. Anyway, thanks for listening.